Okay, we're in section 1.3 now, and we want to look at applications of these systems of equations. And admittedly, again, going back to when you learned substitution and elimination in systems of equations before, you probably saw a lot of different types of applications. So I'm not going to kind of go through those. I can buy 6 hot dogs and 3 hamburgers for $12, and I can buy 2 hot dogs and 8 hamburgers for $16. How much does it cost for a hot dog and a hamburger? And we understand those types of problems can be solved with a set of equations and then solved it with substitution or elimination, or now Gaussian elimination or Gauss-Jordan elimination. So I want to look at a slightly different, more algebraic mathematical type of application. There's actually 2 of them in this section. In this video, I'm going to go through one of them, which is called polynomial curve fitting. The other one, I'm actually going to leave up to you using Kirchhoff's laws. But the idea is, here we're going to kind of start by, I'll give you the answer, and then we'll see if we can actually get that answer using this trick. So the goal here is to find a way to algebraically generate this polynomial if I'm given these points. And right before I did this video, I checked. If I plug in 1 plus 5 is 6 plus 2 is 8. If I plug in 2, 4 plus 10 is 14, 15, 16. If I plug in 3, 9 plus 15 is 24 plus 2, 26. So these 3 points are definitely on that quadratic. And the idea is, if I'm given a bunch of points, can I find a polynomial that will go through those points? And there's a rule that says, if I have, in this case, 3 points, n points, then there's exactly one polynomial of degree n minus 1, or it could potentially end up being less than that. You could end up having zeros in your leading coefficients, leading powers. But there's exactly one polynomial of degree n minus 1 or less that will fit those points. So essentially, using this system of equations and these 3 points, I should be able to generate that polynomial. And I haven't actually tested this yet, so we're going to see in this video if this actually works. And if it does, then I'll just pull another problem from the homework problems, and we'll work through that as well to make sure we get the idea. So, suppose I'm given 3 points. Then I need a polynomial of degree n minus 1, n is 3, so I need a polynomial of degree 2. So I'm looking for a polynomial of degree 2, so I'll just say a sub 0 plus a sub 1x plus a sub 2x squared. And I need to find a sub 0, a sub 1, and a sub 2. So what I do is, I generate a system of equations by plugging these points in here. When x is equal to 1, I get a sub 0 plus a sub 1 times 1 plus a sub 2 times 1 squared should equal 8. When x is equal to 2, so a sub 0 plus 2a sub 1 plus 4a sub 2 should equal 16. When x is equal to 3, a sub 0 plus 3a sub 1 plus 9a sub 2 should equal 26. Now I have my system of equations, solve it. And here we'll actually write it as a matrix and do all the elimination. So, written as a matrix, I get 1, 1, 1, 8, 1, 2, 4, 16, 1, 3, 9, 26. And let's see, first I will do, here I already have a 1 here, so I'm going to have to get rid of this one and this one. So to get rid of this one, I will do negative 1, and actually I'll write it the other way. I will do r sub 2 plus negative 1 times r sub 1, and that will go into r sub 2. Which will give me, the first one will stay the same, 1, 1, 1, 8. The second one, negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 1 is negative 1 plus 2 is 2 minus 1, 1. Negative 1 times 1 is negative 1. 4 minus 1 is 3. Negative 1 times 8 is negative 8. 16 minus 8 is 8. and then the bottom one stays the same. And I will actually take this moment to point out, when we're writing these things out formally, and we want to write them out formally, you have to do these operations one at a time like this. But once you understand what you're doing, I have not affected the third row at all. But I understand I'm going to multiply this one by -1 and then go from there. And if I want to do those in one shot to save time, that's completely fine. Right now I'm not doing it because I'm writing these things out formally, and I want to make sure you can write them out formally. But ultimately, to save time, yeah, I'll do the operation on this row, then I'll do the operation to get rid of this row and do it in one shot. So now, third one, and again, I'm going to do r sub 3 plus -1 times r sub 1 and put that into r sub 3. First row stays the same, 1, 1, 1, 8. Second row stays the same, 0, 1, 3, 8. Now, -1 times 1 is -1, -1 plus 1 is 0. -1 times 1 is -1, -1 plus 1 plus 3 is 2. -1 times 1 is -1, -1 plus 9 is 9 minus 1, 8. -1 times 8 is -8, 26 minus 8 is 18. Now I have the first column done. Work on the second column. Here I actually already have a 1, which means I'm good. I'm not going to worry about reduced row echelon form here to save time. So I'm good with the 1 here, which means I just need to get rid of this 2, and then I should be good to go. So here, what am I going to do? We'll just go down here. I'm going to take r sub 3, and I'm going to add -2 times r sub 2. And I'll put that into r sub 3. Make this a little bit bigger. And again, first row stays the same, 1, 1, 1, 8. Second row stays the same, 0, 1, 3, 8. Now do 0 times -2 is 0 plus 0 is 0. -2 times 1 is -2. -2 plus 2 is 0. -2 times 3 is -6 plus 8 is 2. -2 times 8 is -16. 18 minus 16 is 2. Now, let's see. This is good. This is good. Here, just to make this official, I am going to do 1/2 of r sub 3 and put that into r sub 3. Make this a little bit bigger. And I get 1, 1, 1, 8, 0, 1, 3, 8. Here, multiply this by 1/2, I get 0, 0, 1, 1. Now, read off my solutions. In this case, this is a sub 0, this is a sub 1, and this is a sub 2, based on the way we wrote this. So, this tells me that a sub 2 is equal to 1. Now, backwards substitute. A sub 1 plus 3a sub 2 is equal to 8. A sub 2 is equal to 1. So we get a sub 1 plus 3 equals 8. So a sub 1 is equal to 5. Backward substitute again. A sub 0 plus a sub 1 plus a sub 2 is equal to 8. So a sub 0 plus a sub 1, which is 5, plus a sub 2, which is 1, is equal to 8. 5 plus 2 is 6. Subtract it. A sub 0 is 8 minus 6, which is 2. Now, write out my polynomial. I get a sub 0, which is 2, plus a sub 1, which is 5x, plus a sub 2, which is 1, x squared. And there's my polynomial, x squared plus 5x plus 2. x squared plus 5x plus 2. Admittedly, it's in reverse order, which doesn't matter. And could you have solved this flipping the powers around and starting with the leading coefficient? Yeah, I just chose to do it this way, mostly because that's the way your book does it. It doesn't actually matter which way you choose to do it. But again, I'll do one more just so we can work through it all and make sure we understand how this works. And I'm going to restrict myself to another quadratic from your book. You can do it with a cubic, but you just have 4 points, which means you'd have an extra equation in there. And the Gauss-Jordan elimination and the Gaussian elimination, whichever one you chose to do, would just take longer and more space. And I'm kind of limited on space on this board. I might switch to one of the classrooms to make some of the videos for some of the longer algebra we have to do. But you all understand the principle and the method is the exact same. It just takes longer. So let's see. 2, 4, 3, 6, 5, 10. I have 3 points. N is equal to 3, which means I need a polynomial of degree n minus 1, which is 2. So my polynomial will be a quadratic a sub 0 plus a sub 1x plus a sub 2x squared. Now I create my system by plugging in. When x is equal to 2, I get a sub 0 plus 2a sub 1 plus 2 squared, which is 4a sub 2, is equal to 4. When x is equal to 3, I get a sub 0 plus 3a sub 1 plus 9a sub 2 is equal to 6. And when x is equal to 5, a sub 0 plus 5a sub 1 plus 25a sub 2 is equal to 10. Now with this, write out the matrix. 1, 2, 4, 4, 1, 3, 9, 6, 1, 5, 25, 10. And now, since on the last one I wrote it out formally, here we'll kind of shortcut a little bit. The first row is going to stay the same. 1, 2, 4, 4. Now I'm going to get rid of the 1 right here. So negative 1 times the first row. I'll write these out separately, but we'll do them in one shot. So I'll do r sub 2 plus negative 1 times r sub 1 and put that into r sub 2. So negative 1 times 1 is negative 1 plus 1, which is 0. Negative 1 times 2 is negative 2 plus 3. 3 minus 2 is 1. Negative 2 times 4, negative 1 times 4 is equal to negative 4. Plus 9, 9 minus 4 is 5. Negative 1 times 4 is negative 4. 6 minus 4 is 2. Now, in a different color, we'll deal with the third row. So we'll do r sub 3 plus negative 1 times r sub 1 and put that into r sub 3. So again, 1 times negative 1 is negative 1 plus 1 is 0. 1 times negative 2 is negative 2. 5 minus 2 is 3. 1 times negative 4 is negative 4. 25 minus 4 is 21. 1 times negative 4 is negative 4. 10 minus 4 is equal to 6. Now, we'll work on this column right here. And in this case, again, just so we can go back and forth with the different ways we write this, now we'll put it in reduced row echelon form. 0, 1, 5, 2. So first, I'm going to get rid of the 2 up here. So I will do r sub 2, let's see, we're doing the top one. So r sub 1 plus, to get rid of this 2, multiply this by negative 2. So negative 2 r sub 2, and put that into r sub 1. So I get, the 0 is just going to remain 0 right here. Where was it? Yes. 0 times negative 2 is 0 plus 1, which is 1. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 5 is negative 10. Negative 10 plus 4 is negative 6. Negative 2 times 2 is negative 4. Negative 4 plus 4 is 0. Now, I'll get rid of the 3 down here. So I'll do r sub 3 plus negative 3 times r sub 2 into r sub 3. Negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 5 is negative 15. 21 minus 15 is 6. Negative 3 times 2 is negative 6. Negative 6 plus 6 is 0. And now, we were working on the Gauss-Jordan elimination, but here we're going to kind of shortcut it. I'm going to make this one a 1, and we'll see why in a second. So the top will stay the same. 1, 0, negative 6, 0, 0, 1, 5, 2, 0, 0. Here I'll just multiply R3 by 1/6. One sixth times 6 is 1, and that's still 0. And now what does that mean? Well, if I write it out, I get, let's see, I wrote this as a sub 0 first. So a sub 0 minus 6 a sub 2 is equal to 0. A sub 1 plus 5 a sub 2 equals 2. And a sub 2 is equal to 0. And I actually do stress this. When you see this, this does not mean there's no solution, even though I see the 1 and the 0. If it was the other way, 0 and 1, then it would be, because I'd have 0 plus 0 plus 0 equals 1. But here, this just would say that a sub 2 is equal to 0. But if a sub 2 is equal to 0, well then right here, that goes away and I get a sub 0 equals 0. But then this goes away and I get a sub 1 is equal to 2. Because all those a sub 2's are just 0. Now if I write out my polynomial, p of x is equal to a sub 0, which is 0, plus a sub 1, which is 2, times x, plus a sub 2, which is 0, x squared, which of course then reduces to 2x. And I'll point out two things. One, once we have the solution, if you didn't see it right away, that's actually obvious. 2, 4, 3, 6, 5, 10. All I'm doing is doubling the x's. But again, kind of like I was saying at the beginning, it is not a rule that if you have 3 points, you get a polynomial of degree n minus 1, in this case 2. You get one distinct polynomial of degree n minus 1 or less. But you don't know that going in. Again, here, if you had actually looked at it and thought about it, it was pretty obvious. But in general, as you have more and more points, you don't know what type of polynomial you have. But all you do know is you take the number of points that you have and you start with a degree 1 less than those points. 3 points, polynomial of degree 2. Then you do all the Gaussian elimination, get a solution, then when you plug in, you can actually see the type of polynomial that you get. And the good thing is, again, you can check it easily, just make sure it gives you the points it's supposed to. Like I had said, I'm only going to do these type of applications. The other applications, I'm going to let you people mess around with because I think you will enjoy them. If there are any questions, feel free to ask. And again, I do stress, I know there's a lot of, we'll say, basic type of applications that you have seen before with systems of equations, again, hot dogs, hamburgers, things like that. I'm deliberately skipping over those because, and your book doesn't even have them in it, because you've seen them before, and I don't want to keep doing the exact same thing. I want to see all that we can actually do mathematically using these systems of equations and matrix operations and all of that. So be aware you should know how to set up and solve those, but I'm taking it as a given that you do know how to set up and solve those because you've done it before. We're just jumping to the more mathy and fun type applications.